Okay, so we'll be starting the live feed now. All right. Good morning, everybody, or good afternoon, good evening, depending on where we are. This is the second session of this S20 policy webinar, where we continue to talk about various aspects of astroinformatics. And we have again more great talks and panels lined up. And we'll be, as you can see in the agenda here, I'm going to stop sharing now and introduce the first speaker. So the first speaker in the session is going to be Professor Alex Saleh from Johns Hopkins University and Institute for Data Intensive Engineering and Science. But he was also very instrumental in starting the entire VO activity, and also before that with Sloan and the databases and so on. And he's going to talk to us about the impact of astroinformatics. Alex, please take it away.
Yeah, thank you very much. It's an honor to be invited here. So I would like to talk about the journey of the last 20 or 30 years almost that we went through, and how basically the emerging field of astroinformatics has actually impacted quite a lot of areas way beyond astronomy. And what we see is, so I would like to talk a little bit more about the general pattern that what is happening in sciences, of which actually the whole astroinformatics was embedded in. So essentially, we are moving from the era of manual production of scientific data in small-scale experiments to the Industrial Revolution in big science. And this actually started, so when we look back to the last century, so in the 1920s, science was typically done in small experiments, done by individuals, small groups, and they were slowly growing in scale. And then after the World War, during the World War, there was the Manhattan Project, and as a spin-off of it, we started to establish national laboratories and starting big projects on the scales of billions of dollars. And this typically, simply by the sheer scale of things, they are costing billions of dollars. They take decades to construct the facility. It has to be done in a very risk-averse fashion, typically with a heavy government involvement in every step of the process. But also, as interesting consequence, the data as a result have much longer lifetime. And the fact that, one can look back and see this journey, that we had the Van de Graafs at the turn of the 19th to 20th century, then slowly followed by this first cyclotron in Cambridge. And then we built synchrotrons, and then built the national laboratories. And it was growing in every step of this process. It was growing in scale and ambitions. And then there was the alternative between either a single country trying to build the next big accelerator in the world that was supposed to be the superconducting super collider at SSC, which in the end, even the US didn't have enough resources to build, or build the LHC, which was an endeavor for the whole world. And basically, once we go into this big science scale, it makes also a huge difference. So in the past, when we had these small experiments, they rapidly followed one another, and the data sets had a very short lifetime because they were superseded very quickly. But today, when we build the big science experiments with the billion-dollar budgets, that takes, again, 20 years to design and construct the experiment and another 20 years to run. These data sets may not be surpassed in our lifetime. So the data is here to stay for decades. But today there's another thing happening. So for a long time, science was in this bimodal, and what we see today emerging, there's a much more happening in the middle. And many of these first projects in this scale actually started out in astronomy. You can think about just the Zwicky or the Sloan, or we have seen the Penn stars. So, and the NSF is also recognizing now this, so does the NIH, or even NASA with the MIDEX projects. And these are typically private collaborations and public-private partnerships. Or, for example, the Human Genome Project, which also started in the early 90s. So there was a national scale project, but there was also done by a private enterprise. So the typical pattern for this is to create a unique instrument, use cutting-edge technology, take risks, push budgets to the limit and beyond to maximize science, and generate large amounts of data. And I think you already heard the talk on Sloan. And when we started out, then the budget was supposed to be about $25 million. And then gradually, of course, over the years, it also grew into a 20-year experiment, but this is now in the fifth incarnation. So, but as a result, these projects have a much higher level of agility than the big science projects, because it involves typically fewer people, and they can stay much, much closer to also the technological bleeding edge. And so they represent today, in my mind, the sweet spot for science. So, there are only so many things you can do with a $300,000 grants, and there are many things that you cannot do with $1 billion projects. For example, you cannot take too high risks because the cost of failure could be just too enormous. So you have to freeze the technology very early on. But in these mid-scale projects, so typically, because it's the sweet spot of science, people are also very hungry and aggressive about their science. So they typically don't try to overdo the infrastructure. They try to focus on spending every dollar on getting the best scientific results out of it. So therefore, as a result, they also want to try to save on the computing. They try to do computations on a shoestring. So in general, I have seen on many of these projects, they try to do the computations opportunistically. So they take the data wherever they can get cheapest computations. And AI is emerging everywhere. And there will be, this will be a recurring theme throughout the talk, how AI is actually also changing how we do science. But in this new model, there is much more focus on generating and sharing novel data than any time in the past. There is an issue about agility versus tenacity. So we see extremely agile changes in the industry. So at Google, Facebook, Amazon, Microsoft, the big four. And at Google, the group doing AI and heavy-duty machine learning, so about 8 to 10 years ago, consisted of 15 people concentrated around Jeff Dean. And today they have of the order of 10,000 people all over the world. Can you imagine either a university or even a national laboratory growing a group on that scale? It's impossible. So it's beyond what we can do. At the same time, the attention span in the industry for science is spotty. So many of us collaborated with, some time in our projects with Google, Amazon, Microsoft, and so on. And there the pattern is that there is somebody who is interested in science, who has a good background, is interested to put in some company resources to work with the scientists. But typically after 5 years, these people move sideways. And then suddenly somebody else comes to their place who has no interest or has some other interests. So typically then all this investment go astray and we are just dropped on the floor. So it is clear that the attention span for science is spotty, and there is a ruthless competition related to AI. So they are each watching over their shoulders what the others are doing and running not blindly, but running forward in a very aggressive fashion. So we cannot compete in agility. Just to say, notice that faculty hires are for 40 years typically. So this doesn't mean that we can hire 10,000 new faculty in AI. But we can compete in tenacity and unique high-value data. So how can we create, Sloan-like data sets in other areas of science, not just astronomy, but in medicine, and various, so in fluid mechanics related to large numerical simulations, but that the industry just doesn't have the patience to do. And there are more and more mid-scale projects at universities. So they build a new electron microscope or buy a new electron microscope, but put some interesting new twist on it in terms of data processing with a rack of FPGAs and so on. And they can create kind of almost desktop science, which is groundbreaking. And then we typically use AI to interpret the data to discover new patterns and new phenomena. And this requires also the data sets to be AI ready. But if you look back also at the history of AI, many of the big breakthroughs came actually there, even in there from the, for example, from the ImageNet data set. And we have seen the impact of the Human Genome Project or Sloan, or you know, the early transient sky surveys, which paved the ground basically for LSST. So how does computing and data look like in the era of AI? So it's a big change. Hardware used to be the capital investment. That's why we call it hardware. And scientists mostly wrote their own software. Today, it's completely the opposite. Essentially, hardware is becoming a commodity, either a throwaway or rent it or kind of just get it somewhere for free or almost free. But the data sets and the software are becoming the capital investment. So the software technologies change every 2 years. In AI, it's changing faster. We see actually code carpentry emerging. People are trying to do digital twins. Again, much of this actually grew out of the astrophysics community who have done the first large simulations from where we try to reproduce the universe, how the universe looks like from first principles. And the codes need to be ARCO. This term is coming from the ocean community, analysis ready and cloud optimized. So basically that the codes need to be transportable so that if we get some free time in the Google Cloud or in the Amazon Cloud or in Azure or at an NSF supercomputer or at the DOE supercomputer, we can just take the same code and just drop in and it runs. So the software written by our graduate students is no longer good enough. And we need serious software professionals of industrial caliber to start to get engaged with scientists and be part of our projects. So, and you know, this is many of this, and how the data analysis is changing is also undergoing a dramatic transformation. And it's worthwhile actually looking at what happened in the music industry. And this is going to happen in science, like it or not. So now I used to be able to go down to the record store and bought a Miles Davis LP and took it home and played it on my record player. Then the revolution came with iTunes, where I still had to buy, and I was owning a digital copy of a song, and I had to download that song onto my MP3 player, and I still played it on my own device, and I actually owned the digital copy of the data. But what is happening today with Spotify and Pandora, that everything happens in a way detached from me in the cloud, and I only get a stream of the results. So what are the data equivalents, how we deal with data today? So we basically still download all the data. So this is when we send tapes or disks or a sneakernet computer, this is equivalent of actually buying a hard copy of the record. And we take it home or get it shipped to our homes, and then we run it on our own, the computation on our home computer. What is the iTunes equivalent? This is where we are today with our SQL databases, where we have a large data repository, but we don't have to download all the files, but we can issue a SQL query, which gets our data, what we need for our next paper, kind of one song at a time. And this is how basically many of the astronomy archives work today. And what is happening is kind of the Google Colab and SciServer, that is the Spotify Pandora equivalent, where basically we do all the processing in the cloud, the data sits in the cloud somewhere, be it a private or a public cloud, and then we just play with it and we get the result. So, and we are in between today, as we can't afford to keep the data in the cloud, but it's kind of inevitable that the economies of scale will change. So how did I get here? So I got involved in 1992 into the Sloan Digital Sky Survey, which started at the same time as the Human Genome Project. And at that time, the scope of the project was 25 million. So it really fit, and it was managed by the few universities. It was really fitting very nicely the mid-scale projects in between the individual grants and the billion-dollar large projects. And for various reasons, the project actually, we grossly underestimated the cost of the project, but in particular, the cost of the data processing and the software. And so it took twice as long than we originally anticipated. But there was actually a helpful outcome in this, because in the meantime, Moore's law and Kreider's law came to the help. The price of disks went down by a factor of 2, and the computers every year, and the computers became twice as fast every year. And so we were able to do a much more ambitious job on the data processing and how we preserve the data than we originally had any right to expect. And it was a privilege to work with Jim Gray in this through all those years, and who helped us, the whole astronomy community, not just Sloan. He was actually involved in the whole broader Astroinformatics effort. And he came to our meetings and provided a lot of very useful advice, which we are still living with today. But what we saw in particular, that the usage of these systems resulted in the emergence of the internet scientists, and that were, once we presented data in a nice shrink wrap way on the cloud, in this iTunes way, then it was not just professional astronomers who used our data, but actually a lot of people who had an interest in science, computer gamers or school teachers, made some really major original discoveries in astronomy. So, but it came up, why is astronomy interesting? And why was it easy to actually get the whole astronomy community lining up for this? And Jim, so it's important that astronomy has always been data-driven. We can't do laboratory experiments. We can't go to the lab, twist a dial, and suddenly a star goes ping on the sky. This is beyond our experimental capabilities. So all that we can do is come up with new ways of observing the sky and derive our hypothesis from the data. And this is now becoming more accepted in other areas as well. And this is a picture of Jim Gray at Microsoft talking about how big the astronomy data is compared to, back in the 90s, we actually were really leading the world in some data sizes. And Bill Gates was asking him that, why do you spend half your time working with astronomers? And Jim said, I love to work with them because their data is worthless, meaning that it has no commercial value. So we were able to do experiments which otherwise, from conflicting commercial interests, would be prevented. So we didn't have to sign non-disclosure agreements with the Microsoft lawyers and so on. We could just really share the data with anyone who was interested. And this was a lovely way to work. And so this is our institute at Hopkins, where we try to take all the things that we learned on Sloan and astronomy and try to provide disruptive assistance to a whole range of science projects. And we basically try to recognize consciously the patterns that we saw over the last 20 or 30 years that we have been working on this, and translate them into processes that we can deploy in other areas of science. So, and how can we take these lessons learned and apply them in a multidisciplinary setting? And first of all, it's important to see that the science engagements have distinctive phases of maturity. And we also have a similar valley of death like startups do, that when we have to take a project from prototype to actually a production and get a community acceptance. There is a several years gap there where we have to have enough funding to actually carry us through until we earn the trust of the community. So trust is very hard to earn and very easy to lose. And so in the end, we actually created, and we took the Sky server that we built for Sloan and turned it into the Sci server with the NSF's help, where we kind of took it apart and put it back together in such a way with a much cleaner API, and we isolated the astronomy-specific parts into one corner, but modularize much better the rest of the core so that we can plug in other modules for different science domains, medicine and turbulence and ocean circulations and even digital sociology. And so currently we are hosting about 30 petabytes of data and 200 servers, and we have over 10 million casual users and 10,000 power users, but in a very broad range of sciences. And we are operating at a pretty good economies of scale. And this is what is important for a university, where we are always short on money. And these are, so basically, in a sense, if I wanted to have a single sentence description of what the Psi server became, it's a scalable data aggregator. It's very difficult to aggregate data sets, and there are many mistakes people make in the commercial or in the government world, where they try to, when they bring in multiple data sets, they try to create the data fusion and data federation. The most frequent mistake is trying to create the mother of all databases, to try to tie everything up with everything. And this is unfortunately a combinatorically complex process. When you bring the second data set in, okay, you build the links between the two data. You bring in the third one, you have to actually build the links to the other two, and so on. And this gets harder and harder. If you have n data sets and you bring in the n+1, you really have to build for each new data set n+1 connections. And this doesn't work. So we adopted a very different philosophy that works really well in keeping it simple, that we require that every new data set we bring in has its ontology and in a very self-consistent way and well documented, and so that our users can actually make these associations and links between the data sets, because also, bringing in two different astronomy data sets, no two astronomers will want to do the cross-matching the same way. And this is true, and we see this pattern repeating everywhere else, also in medicine. But the most important thing is that people are able then to share these value-added associations with each other so that we can build a collaborative aspects into the data. And such a way we can keep the complexity of the system linear. So it's the same cost adding a new data set. It's not increasing with the complexity of the system. And so here are, starting from Sloan, we actually built now the world's largest simulations database for turbulence, and it is now picking up. And as of a few weeks ago, we delivered 181 trillion points to the world. This is, again, working in the iTunes metaphor, but basically people can insert in the simulations virtual sensors that from a laptop, which simply do measurements in the simulation and send back a data stream to the user. And you can have these sensors move with the turbulent flow and send back the trajectory and the temp and the pressure and the dissipation rate and vorticity, for example. Then we built recently the AstroPass, which created a 1,000-fold increase in cancer immunotherapy. And we are in the process in building one of the world's largest ocean circulation model. So let me just do one slide on this. So basically, the idea is to do multiplex imaging, so many color, 45 color imaging of the cancer tissue, and do a similar mosaic as we did on the sky. Then we do a segmentation on this data, again, just like we did in astronomy, we do this. And then we build a spatial database to study essentially the interactions between the immune system and the cells. And there is a remarkable similarity. The atoms of the universe are the stars and galaxies. And for a cancer tissue, it is the different type of cells, cancer cells and immune cells, and so on. And then we are actually now running all sorts of machine learning and AI projects on top of this. And so this is really taking off in a fantastic fashion. So the lessons, what we learned over the years. If we have a big, powerful database with spatial features, essentially it's much easier to work than with a large set of flat files. It doesn't matter whether it's a relational database or a key value store or a NoSQL. But we also need to go beyond SQL in scripting. We need to, and Jupyter came just in time, and so to make the bridge, build the bridge between these data sets and deep learning, everything is spatial. When we build these data sets, automation is essential. If we have a few human steps in the process, that is going to kill scalability. We always need the deep links to the raw files, so we need to be able to go back and validate if you find something interesting, that this is not an instrumental artifact. And building a trust is the key. So how can we actually do something that is consistent, not changing, and over the years, and people basically start to rely on it and work with the community to establish basically the quality measures of the quality of the data. And the important thing is, do not try to do everything for everybody. Figure out what you want to do, and it is just as important to figure out what you don't want to do. And how can we turn this into practice? What we see is basically we need to figure out the right trade-offs, and how can we protect the data, and how can we still allow enough creativity to actually do interesting new things that nobody thought when they were designing the system. And there is a critical human infrastructure. So we need to have architects who work with the scientists to help them to translate their problems, their challenges into the architectural solutions. We need to have implementers. And once we build a system, then the disruptors come in who figure out completely unexpected ways to use the system and make new discoveries. And then we need the trainers who then teach these new methods to others to actually have a widespread audience of users. And then we need to create a sustainable model for the infrastructure. How can we protect this data, which have now going to have a lifetime of many, many decades, possibly. And we need to innovate in data collection. So I'm starting to run out of time, so I'm just going to try to do this very quickly. How can we measure the future usefulness of data? And there are these three aspects: the cost, the price, and the value. What is the value? Okay, we all know what the value of the data is, but how can we translate it into dollars? Basically, it's about publications. How many publications use the data? And when you think about a typical NSF grant in astronomy is about 300K for over 3 years. So if they write one referee paper a year, that costs a paper is about 100K investment of research money. So if a paper is using an existing data set, it is a $100,000 vote on the utility of that data set. Okay. What is the price of the scientific data? How much did we spend on the experiment over the years to actually get that data? And this is the only manifestation, of the final data set is the only remaining legacy of that experiment once the instrument is shut down. So a new electron microscope is between 10 and 50 million. Over the 20 years of the Sloan's existence, we spent about $200 million. Rubin will be over $1 billion, and CERN, LHC, and James Webb and Hubble, they each were probably well over $10 billion. So all that remains for this investment at the experiment is the data. And what is the cost? How much does it take to actually preserve year to year once the experiment is shut down? And so basically, this is not just about the disk. These are all the dead drives in Sloan, 1.1 tons of hard disks that failed over the years. And so, but this is the easy part. The hard part is actually to keep on the corporate memory of the project, that people remember what was what and take care of the documentation and update the services, update the operating systems and so on. These are smart services, so it's not enough to put the data just on disks anymore. So there has to be a trusted intermediary between the data and the scientists. And so when we compare it for Sloan, the cost of running the Sloan archive is about $500,000 a year. We paid about $200 million to get the data, and the value is about 100K per paper. We have 10,000 published papers based on Sloan. This has a value of $1 billion. At the cost of producing it was $200 million. Okay, So if the community only publishes 5 papers a year, then the cost of keeping the archive alive is actually on par with the gain. And if you compare it to the cost of getting the data, it's 0.25% per year to maintain the archive. So I think I was actually pretty blown away when I first computed this number. And it looks like it's similar for LSST or for other projects. So Sloan is not alone. So 5% of the survey price would cover the data for 20 years. Think about this. Okay, and the last bit is prioritizing for relevance. Do you have enough data or would you like to have more? No scientist would say, I don't want to have more data, but it's the wrong answer to an ill-posed question. Why? There is a delicate trade-off between the scientific value and the preservation. So in one extreme is that store everything, gobble up everything, and go bankrupt because all your budget goes onto disks. The other extreme that if we collect too little data and throw away much at the detector, it's not enough for the science. And the LHC provides an interesting lesson. So they basically have this accelerator and the rings and the colliding rings, and they have a couple of beam lines where they put in their detectors and they throw away almost all the data. They keep only 1 in 10 million events. And this is still 10 to 100 petabytes. So they try to have these in situ hardware triggers. Now they are running actually on neural nets to capture the new science, but throw away everything that we know about. And this is what we need to do in science. We are basically crossing the point where we can afford to store everything without thinking about. And we have to focus on how can we actually get more and more relevant data. And we each have to figure out, again, this trade-off, where is it 80% of the science value carried by 20% of the data, or is it 99 to 1 or 999 to 1? We are probably not at the extreme of the LHC. So what is the next? How can we take more relevant data that we basically start, trusting the decisions, more and more of the decisions on AI? So we are trying to work on this with the help of Eric Schmidt. But essentially, the bottom line is if we let AI drive our cars, it can drive our microscopes and telescopes as well, to actually figure out the best way to what to target with the high-value experiments. Okay, finishing. So open big data is at the forefront of all science. We see a convergence between physical and life sciences. Most of the disruptive technical changes keep happening, and it's not over yet. It's going to happen for the foreseeable future. And we made up much of the strategy as it happened. And again, this is what we are still doing. The federal funding has been much slower and mostly reactive. It's always fighting yesterday's wars. And this is where I think the governments have a little bit more vision on the government side would be an enormous help. It turns out that much of what we learned in astronomy, much to my surprise, was remarkably applicable to medicine and many other disciplines. And astronomy and astroinformatics has been at the bleeding edge of this process, primarily because we have very little commercial interest kind of blocking the free sharing of ideas and data. So what are the challenges ahead of us? Who will be the trusted intermediary for our data? How can we train enough people to modern AI techniques and retrain them every 2 years as the world is running forward? How can we make ourselves more agile while we keep the good thing about being persistent? And how fast can we reinvent ourselves over and over? And so I think it's appropriate to call Lewis Carroll here. Now here you see, it takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast as that. I don't know how we can run much faster than the way we have been, but it seems like we still have to do that. Thank you very much.
Thank you very much, Alex. Very insightful. So we have time for just maybe one question. Anyone online wants to unmute and ask a question, perhaps? Otherwise, I would make a comment and sort of semi-question. So what happens is that you describe these different projects, how much money that they spent, how many people they had, and all that. And the parallel that I was thinking of are data sheets and model cards are for machine learning algorithms. Maybe we need to make such cards for each of these experiments, be able to have the metadata for each of these experiments and see how they compare with each other and have that publicly available. Maybe that's
Yeah, I think that would be a very good idea and extremely useful, I think. Because I think it came to me as a shock when I put these numbers together, how cheap the data preservation is, and you know how little interest there is, you know, from our funding agencies to do that. And this will remain until one of the major scarce surveys or one of these data sets screws up, and then a lot of data will get lost. There will be a scream for murder, and then finally there will be actually some action. And it would be nice not to go through that.
So, Rennie, I see that you turned on your camera. Did you have a quick question?
Yeah, I guess just a question would be, this is really, really fascinating. But if you could start again, what would you have done differently? You've talked about great lessons that you've learned, but what do you think, you could have done differently?
Yeah, I don't think we could have done things much differently because it was largely, you know, tackling the unknown. And right now, if you ask me what should we do differently, that what to make the world a better place in 5 years, I don't know, because it's changing so fast. You know, we are running as fast as we can, and we still can't figure out in many ways. But that's also the beauty of it. So.
Thanks.
All right. Thank you so much, Alex. And we need to move on. The next talk is going to be by Vanessa McBride. She's from the IU Office of the Astronomy for Development, and she's going to talk about astronomy data for development. So please take it away, Vanessa.
Thank you, Ashish, colleagues. Okay, so you can see my screen?
Yes.
Okay, so thanks very much, Alex, for that fantastic walk through some of those projects. I think today I'll just kind of give an overview of our ideas of astronomy for development, and of course the role that that data can play in that development. So I'll give a brief overview of astronomy for development, why data, and then some examples maybe to trigger our thinking of what is the potential for data and data skills to push development. So just sort of zooming out to the big picture of why we're having these meetings anyway is really because while there's a lot of exciting things happening in the world, there's also some issues that are being generated, and we can see this if we just look at the news every day. We've got issues of growing inequality. We've got issues around development of these new technologies. We've got all of this happening against the backdrop of global warming and climate change. And of course, all of this as well amidst these rising geopolitical tensions. So it's quite clear, I think, that taking a broad outlook, there's significant challenges as well that's facing us as a sort of a global community of citizens on Earth. And so in terms of astronomy for development, our focus is really that kind of broad definition of development, which is maybe most easily captured in the global goals for sustainable development that have been brought together by the United Nations and have a whole set of goals that you can see here in this colorful diagram and targets related to those goals that are hoped to be reached by 2030. And these goals cover things like reducing poverty, improving the health and well-being of the populations, growing industry, innovation and infrastructure, reducing inequalities, and then global stewardship of the climate, of life and biodiversity. So it really covers an incredibly broad range of things. And I think sometimes it can be a challenge to think about what is the role of astronomy in these kinds of problems that are really focused very much on life on Earth. But with a bit of brainstorming, it's not that difficult to come up with some very obvious overlaps. And here are just a bunch of sort of astronomy related initiatives that have the potential for impacting on these very big and ambitious sustainable development goals. And of course, one of these that I've highlighted in the yellow box in the bottom is around the potential of astronomy and of course data analysis skills to provide impetus in terms of work and economic growth, even in areas outside of astronomy. So just to kind of bring a focus on astronomy, I think, as Alex said in his talk, really astronomy has been at the bleeding edge of technology development. And in a sense, astronomy is there because, you know, we're asking some of the big questions in terms of science and research. You know, is there life on other planets? You know, how did the universe form and evolve? These are really huge questions that are of relevance not only to astronomers, but of course to the global population. And it's one of those kinds of questions that, you know, really resonates with people broader than astronomers because of that relevance. But in order to answer those questions, you know, we have to have technologies, we have to have data, we have to have algorithms that really are at the cutting edge of technology and pushing those frontiers. And so we think that astronomy is a particularly powerful tool for development because it encompasses these three key aspects. It encompasses the science and the research, which by definition is multidisciplinary, ranging from physics, from chemistry, from computer science and maths, encompassing the technology, all of those various aspects, but also has that very real sort of broader relevance philosophically, a sense of promoting global citizenship, and, you know, a lot of cultural significance in terms of connections with our roots for a lot of different cultures on the planet. So these kinds of three factors really bring home astronomy as a potential tool for socio-economic development. So now I'll just chat a bit about the Office of Astronomy for Development and what our goals are. The office has been around for just over 10 years. It's an equal partnership between the International Astronomical Union and South Africa's National Research Foundation. And the office is based in Cape Town in South Africa. And really it has just a very simple sort of baseline philosophy, which is to try and use astronomy to make the world a better place. So whilst the office is based in Cape Town, the office also has 11 regional and language nodes distributed across the globe. You can see the footprint of those language and regional offices here. And the idea of these is very much that, you know, as a varied population and with varied development goals, it makes sense to have regional offices that can respond to the local issues in those areas. So for that reason, we've got a sort of a global plan that unites the goals and the overall strategy of the regions, but we also have specific regional offices that can respond to things on a more regional level. Of course, all of the work of the Office of Astronomy for Development would not be possible without the partnerships. You can see in this slide some of the sort of past partnerships that we've had in the slightly muted tones, and some of the current partnerships that we have. And these partnerships are varied. Some of them are joint awards, some of them are joint staff, some of them are a particular joint project that will be we're working on. And I'll discuss some of these partnerships as we talk a bit more about data and its role in development. But maybe just before going into that, as a big picture around the Office of Astronomy for Development, we have these sort of three flagship projects. And these are projects that we run in addition to our annual call for proposals, which collects a number of astronomy for development ideas, really from the on-the-ground astronomy and associated communities. But these call for proposals projects have been distilled into generally these three themes. One is to use astronomy to stimulate economies. So really how you could use an observatory or something to drive, for example, tourism, dark sky tourism in some kind of area. That's one example. Our Astronomy for Diplomacy flagship at the moment is focusing very much on the global mental health crisis and what the potential is for astronomy in the public to respond to that. And then the third flagship project, probably most relevant for this discussion, is our knowledge and skills from astronomy. And so the idea here is really that across sciences, across development, data can be a common language, and how we handle that data, really those principles, those algorithms are quite transferable. And so that can be a language where astronomers can bridge this gap between sort of research science and science or interventions that have development-related impacts. So just to discuss some of these example projects, in our knowledge and skills for astronomy, we started this off actually initially by making resources available. This was done through an astronomy and data science toolkit, where we used sort of case studies in astronomy just to provide potentially teaching materials in the field of data science and data curation. Some of the others I'll talk through now are data-related education support, hackathons as a way of exposing young people to data science, and of course our goal in initiating some of these cross-disciplinary collaborations based on data, and maybe a future goal in terms of training for infrastructure provision also as part of this knowledge and skills flagship. So to highlight one of the projects, we have a Memorandum of Understanding with the IVOA that's about 2 years old now. It focuses on sort of 3 key areas, looking at the role of the IVOA in blended learning and coursework, looks also at promoting education, and of course in more science for development projects that can be data-driven. And probably the most relevant project here is looking at the IVOA in developing about 10 or 12 virtual observatory related tutorials, which will support a new master's course being developed at the Copperbelt University in Zambia. And so that is an area in which the IVOA and Astro4Dev have been able to support mobility and Drs. Priya and Najama Hassan to visit and to develop these resources that really build data analysis into an MSc course so that it's not a purely theoretical exercise. The second example is relating to these data science exposure hackathons. So this was a project that we started in collaboration with Dara Big Data. I think Kevin mentioned this project yesterday in the human workforce panel discussion. And so this was a project initially started through this partnership with IDEA, which is the South African-based Institute for Data Intensive Astrophysics, the Dara Big Data project, which looks at developing radio astronomy related skills in some of the square kilometer array partner countries based in Africa. And the idea here was really to run these kinds of data science exposure hackathons for sort of senior undergraduate or postgraduate students with some experience of programming, to expose them to some of the data science skills in a sort of a collaborative peer learning environment, and to give them, as this exposure would sort of provide the confidence for them to take the next step, whether that is to sign up for these online courses, or whether it's to consider a data science career, or even potentially a career in astronomy. So this project has evolved over the last few years. We now have many more partners, including the African Astronomical Society, the BRICS Astronomy as well, and it's found a home at the URL hack4dev.org. Some of the philosophy of this project is really around sharing these transferable skills from astronomy to other fields, and of course creating options for career paths for the students who are participating in this, whether those career paths are in astronomy, or to show these students what is available with the skill set they have potentially in astronomy, but in much broader fields. And of course, this has impact on development through the SDGs listed here, through looking at improving education, looking at providing decent work and economic growth, and of course in bringing innovation into this field. So just to give you a flavor of the kind of work or the kind of hackathons that are available, it's quite a broad variety. We've got some that are astronomy based, like the SKA data challenges. One of the first data challenges has been converted into a hackathon. And of course, there's a really nice project around the search for extraterrestrial intelligence and the image classification of galaxies. But those are supplemented with other projects that look, broadly at how you use the same skills really and the same algorithms to classify galaxies as you would to classify apples in terms of which are good and which are bad. So it's a very broad scope, looking both at astronomy but also at related fields that can have an impact on development. And then, of course, one of our key philosophies at the Office of Astronomy for Development is that the kind of magic and the innovation really happens at that interface between different fields. And so how can we work across the boundaries of astronomy and other sciences or other disciplines to spark that innovation and to really have an impact? One of our recent examples has been a kind of getting to know each other in terms of the humanities side. I think Alex also mentioned this around as digital sociology as a potential user of Astroinformatics infrastructure. And so we've had very basic interactions with the South African Centre for Digital Language Resources, are really looking at growing a user base within South Africa for digital humanities and using data science as a potential tool for humanities research, which up until now in South Africa really has a history of being quite qualitative, And so this is an area which has a new potential for collaboration and learning. So just to kind of demonstrate what we mean by digital humanities, this is a plot from a paper by Jonathan Schoots and it's taking scans of newspapers, and these are newspapers from the late 1870s to 1890s, looking at optical recognition and just using very simple algorithms to sort of look at the frequency analysis of certain words. And from that, the inferences are social science results, where they've looked at the ideas of an emerging identity of Blackness that's been catalyzed either through certain events happening around those dates or by the prominence of certain public figures in those debates. And so this is a really sort of a nice example of where we see a kind of emerging field that where there really is a lot happening in the data science perspective. And, this is also an area where even sort of students with a fairly entry-level knowledge of data science and algorithms in astronomy can have a potentially large impact in terms of development. So our kind of philosophy is very much that how we see the impact of these different disciplines on development is in terms of the skills unique to these disciplines. So in the blue line here, you can see, of course, astronomy has big data. It has a really powerful outreach community. How can we mobilize those sort of different skills and qualities to run particular interventions? For example, data skills workshops or communicating science. And how can we put those kinds of characteristics together with things that come from other fields? So in terms of psychology, the expertise or the skill there might be behavior change. Can we combine that with a large outreach community that comes from astronomy to have an impact on communicating science? And that science can be broad, not only astronomy, but potentially have impact as well on things like climate action and biodiversity. So really that's, I think, whilst the sketch looks complicated with the arrows, idea is just very simple in terms of using the particular skills that we have across these multiple disciplines, combining them in particular interventions to really have a broader impact. And for this reason, the OAD is working on a collaboration gateway. And this is really somewhere where we see projects either engaging with people who want to work on projects that have potential for impact in the development world, or where you may even come with a potential research project and initiate a kind of a project where you need external help. And they could be research collaborations either across various different disciplines. It might be a project that focuses on skills transfer. It could be even an optimization of processes idea, or in the simplest form, an on-the-ground support, for example, looking for volunteers. So there's a host of different ways in which one could potentially use this kind of online platform. One way through this green circle is to engage. If you're interested in working on one of these projects through project onboarding, and then getting in touch with the OAD and the relevant partner to implement the project. And of course, in the blue circle shows if you want to initiate a new project, getting in touch with the OAD, preparing an onboarding package, a sort of a project brief and what's required, and then hosting this on the collaboration gateway. So I think I'm happy to round off here, and we can discuss any questions. If you do need to get in touch or have any ideas on astronomy for development projects, or potentially how data and data analytics projects can catalyze some of these development goals, then we'd love to hear from you, and please get in touch.
Thank you, Vanessa. That was excellent. Are there any questions online? So some of the questions that came up earlier today during the discussion were, for instance, when you are trying to get students from multiple countries for projects, etc., there doesn't seem to be a uniform level in which you can judge them if you do not know about people from those countries. That was one thing that came up. And the other thing was in general about how, if there is a large project, how is it that you can do this kind of connectivity? So do you have any broad comments on that?
Well, maybe I can just use the hackathons as an example there. I mean, that's an example where we have, we've asked students for a basic level of programming, but it's very hard to judge before the time whether, A, what is the basic level of programming, and B, if students have that without some kind of a test. So I think with those kinds of interventions, we end up with students all in the same room with varying levels of expertise. And one of the things we do find is that because the hackathons are running in peer learning environments, as I think students find it easier to learn from each other. And so we often end up with if we find that students are not able to sort of cope with the skills they have, then we can rearrange the peer learning environments to do that. But I think it's just part of the, it's part of the the diversity and the joy of working in this area, because it's also rewarding for students to be acting as mentors to their colleagues.
Great, thanks. Rennie, did you have a question?
Yeah, I was just going to ask, you also mentioned that you have these either remote or in-person fellowships. And I guess I just wanted to understand, how do you see, given these kinds of really engaged learning models, do you find that in a remote partnership or a remote fellowship, someone can get the same kind of experience, or do you find that folks engage more with these concepts in terms of in-person fellowships? I know we're not talking about the hackathons now, we're talking about being embedded with different institutes, but I'm curious as the interactions remotely.
Yeah, thanks, Renee. I think it depends very much on what the fellow is working on. So we at the moment have a mixture of remote and in-person fellows. Some of them, I think, they obviously miss out to some extent as a remote fellow, just because, you can't join the office lunches and you can't have that kind of a vibe. But I think it depends very much on both the person and the project. So it's been a bit of a trial period at the moment. Some people work really well remotely and are able to participate and deliver. And I think other people find that, they would perform better, if they were in an environment where they could ask something, in an office space rather than having to type it in an email.
Thanks.
Did anyone else have a question? We have time for, okay, Chris.
Thank you very much, and shame on me for not paying as much attention to the OAD in recent years as I perhaps followed it in its early years of formation. Can you look in your crystal ball, please, and take us forwards about 10 years, and what will a successful outcome from the OAD look like, particularly around these data skills and upskilling communities?
Yeah, I think we've always had these internal discussions at the OAD, and saying that a measure of success of the OAD will be that it no longer needs to exist in the future. And so I think once these kinds of practices become so embedded in the community that they don't need to be driven by the OAD or by sort of key role players, then I think that will be our measure of success.
And do you feel some of the lessons that we've learned through the COVID pandemic and our ability to work remotely and collaboratively, do you think that's having a positive flow-on effect as well, the technological accessibility notwithstanding?
Yes, absolutely. So I think that the OAD was very quick to switch to a kind of a model where, we could just work remotely. We'd also been forced to adopt that kind of stuff anyway, because of the global nature of the work and the regional offices. But, I think we're aware of striking a balance in that, because I think the value of the face-to-face interactions, at least in initiating collaborations, shouldn't be underestimated. But in terms of a mode of work, it's incredibly efficient going forward. So we hope to build that into many different projects, into the fellowships, into our relations with regions. And we've tried a bit in terms of some of these data science exposure hackathons. Some of them were forced to be supported remotely during COVID. So, for example, we'd have a bunch of students in Kenya with tutors, and then we'd be organizing it from sort of Manchester, South Africa. It was, I think, pretty difficult to do that. Those kinds of interventions are much easier to run in person.
Great, thank you.
Okay, time for just one more quick question, if any. All right, if not, let's thank Vanessa and move on to our panel today. So this is going to be on global data, and Jinzhao is going to lead it. So please take it away.
Ashi, it's our time. So can you hear me? Yeah. Okay,
Yes.
thank you. And now we have, please open your camera Rini, can you start a video? Yeah, thank you. So now all the panelists are online here, and following the procedure, first we should have a self-introduction for each of us. As the list, so the first one, Mark Allen. Yeah, please.
Hi, Chenzu. Very nice to see everybody there. So my name is Mark Allen, and I'm an astronomer, and I'm the director of the Strasbourg Astronomical Data Center. It's called the CDS, and we have a role in astronomy for processing data that comes from publications from journals. So we are very much in tune with the sort of data that people are publishing in astronomy. And I've also had the privilege of being involved in the virtual observatory activities from the beginning, and to chair it for a couple of years, and to see how that has an impact on the way we share data in astronomy. So I'm happy to talk more about those things as in the discussion. Nice to see everybody there.
Yes, thank you. And Patria Whitlock. Patria?
Yes, I'm Patricia Whitelock. I'm an astronomer and an honorary professor at the University of Cape Town, and a former director of the South African Astronomical Observatory. My only current formal responsibility is as project manager for the South African collaboration with the Vera Rubin Observatory, which will link data from the Meerkat Radio Telescope at the SAO and the Southern African Large Telescope with the Rubin Legacy Survey of Space and Time. I've also been involved with the IVOA and from time to time with the Strasbourg Data Center. Thank you, Chensu.
Yes, thank you, Patria. And our next panelist is Christoph Flock. Christoph?
Everyone, I'm an academic at Swinburne University in Australia, and because it is NAIDOC week here in Australia, I would like to just briefly acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of the lands that I'm calling in from today. I've had a long time interest in using astronomy big data, particularly through visualization to improve new ways of discovering. And in the last few years, have been thinking very actively about translation of astronomy skills with data into disciplines, including Earth observation and digital health.
Yeah, thank you, Christopher. Rini?
Thank you so much. My name is Renee Lajek. I did my studies in South Africa, so it's great to see so many faces I know very well. And I'm now based at the University of Toronto, where I'm associate professor there. And as of a few days ago, I've become the spokesperson for the largest survey on the Rubin Observatory, the Dark Energy Science Collaboration. And so that will be work sort of bringing together all of the scientific, different scientific interests, and making sure we work well with our international partners, which includes Canada, where I'm currently based, and of course South Africa, as Patricia was mentioning. So I'm really interested in making data accessible to different scientists and researchers and the public, and how we enable the biggest scientific innovations with those data. So thanks.
Okay, thank you all. And from our previous speakers, including Alex, Vanessa, and for example, Ajit Kimpavi, and some other speakers, they already give us many backgrounds for the global data. And so today we prepared a long list of questions. So, and we hope in the following 15 minutes, we can cover quite a part of these questions. Oh, I'm sorry, I should introduce myself. I'm Chen Cui from National Astronomical Observatory of China. and I'm leading the Chinese Virtual Observatory, and now also president for the IU Commission B2 data and documentation. Yeah, I have working together for many years with the IVOA, and so this conference, I meet many old friends and new friends. So let's start our questions. The first one is what are the ways in which global data in astronomy have changed over the last few decades, and what we can expect in the future? Maybe they have, this topic have been mentioned in our previous speakers, but I'm happy to learn more comments from you. Yeah, please.
I can start just while others are unmuting. So I think it's been very interesting that the International Virtual Observatory Alliance has been mentioned quite a few times. I remember as an undergraduate learning about virtual observatory ideas, and at the time it was, you know, very, very exciting, and it was something new. But to some people, you know, who are in a certain mode of, I'm just going to get the data from my telescope and download it and do the analysis, it seemed like it was a fun thing to do, but it wasn't necessary. And now, you know, 20 years later, it's completely changed. There is no world in which you cannot, you know, think about these very large data sets. The world in which you just download the data onto your machine is really over. And so we are forced to think about data connections and the ways in which we understand the formatting and the processing of data as the surveys just get larger and larger and the volumes get more extreme. So I think it's a very interesting shift in the last 20 years just to see the, you know, as we get more ambitious with our telescopes, it becomes impossible to do astronomy the way it was done 40 years ago.
Okay, yeah.
Yeah, I can add to that too. I think we're at the sort of transition point now where a lot of astronomers are going to realize that they just can't download the data that they're going to work on. I think we're not quite there yet. I mean, you know, if you look at one of the successes of the virtual observatory is, for example, its use for the Gaia data, the ESA Gaia mission astrometry data across the sky. So if you have a fast internet connection, you can still download the Gaia data catalogs and work on them on your local computer or cluster. So you can do that now, but when it comes for the next missions or things like Euclid, I think some astronomers are going to get a little bit of a shock that they will not actually be able to do that. And I think that there will be a more realization that you need to work on science platforms and where the data is. But this is also coming through projects like the SKA and through the Rubin project, which has, you know, embedded in it the idea of a science platform and that you would interact with the data somewhere rather than downloading it and having to deal with it all yourself. So I think that's one of the ways in which global data is changing, and that we're at a transition phase now.
It's
Perhaps
interesting. Doug, you go, Patricia.
Okay, sorry. I just to add to that, which I agree with. Basically, colleagues have already outlined that the complexity and the size of data is changing and will go on changing. But it's also worth noting that the speed of data is also changing, and the need to access data very rapidly, and this brings us back to transients and the Vera Rubin Observatory and everything else, that we need to present data to people quickly so that they can respond to it, and in such a way that they can sort out nonsense from effective, useful data. And that will be an ongoing problem with the Vera Rubin Observatory material. but also one of the most exciting things to respond to for the people who are following up on that kind of material. Thanks.
So Patricia, you said essentially what I was going to say, but much more eloquently. So thank you for that. I think it's interesting from looking at astronomy, where initially volume was the problem that astronomy, and I think Alex gave a great discussion of that through how the SDSS grew. And a lot of the early work they were doing was trying to work out how do they even store that data, let alone do anything else with it. And at the moment, astronomy does not have the biggest volume data sets. We will have them again in the very near future, but at the moment, we're not generating data at the rate of other disciplines. And it's that velocity aspect that keeps me awake at night. Can we do things fast enough, even now, to keep up? And it's the time domain and transient astronomy that's really showing us that we do need to make decisions with data very quickly. Otherwise, the value of that data rapidly diminishes.
Thanks for the comments. And you know, the topic for this conference is science and policies for sustainable development. So our next question is, what policy level preparations are needed to address the challenges and opportunities presented by the increasing volume, complexity, and the distributed needs of the age? Yeah.
Can I start on this one perhaps, and we'll go in an opposite order. I think we need policies that don't make it harder for us to share data. I think that's, anything that you do that adds a layer of complexity for a scientist, they're going to not want to do it. So, so I don't know what some of these opposite policies might be. Just as a note of what's happening in Australia at the moment is, like elsewhere in the world, there's a lot of discussion around generative AI and what will happen there, and a lot of government debate around regulation. And sort of, I'm already concerned that you might suddenly over-regulate techniques and ideas that actually prevent us as researchers doing really clever things. And so astronomy can be a great discipline. Picking up again on some of the comments that Alex was making about our data doesn't have commercial value. So policies that allow us to experiment with new ways of sharing data and working with data would be fantastic.
I can see that there's a lot of open science policies being installed in different places around the world, especially here in France and in Europe. So some of the words that they use for that is that, like Chris said, kind of try and remove barriers to the use of data. And they say, make things as open as possible and as closed as necessary. Often when they're talking about that, they're thinking of health data, and when they say closed as necessary, they're thinking about privacy issues. But I see one side on astronomy where some projects have to address the level of their openness, just because the cost of using data, you have to provide computation alongside of that data, requires them to have a certain level of closeness, to be closed at some level. But in terms of policy, I think, it's happening not just in astronomy, but all through science, is that, there should be open access, there should be open data, and they're referring not only to, for researchers, but for the public to see that the money spent on research is somehow accessible to them. And I think we've got lots of good examples about that in astronomy.
Yeah, perhaps I can come in and make some comments about the situation in South Africa. I should first say that Bernie Fanaroff is talking later today or tomorrow, depending on where you are, about the radio astronomy side of things. So maybe I can more easily talk about the optical side of things. There are certainly policies for open data in South Africa. At the moment, they have mainly been focused on publications and data from publications. There is not yet a full appreciation of the broader need for openness of all data that comes from telescopes. But I think our strongest problem is the lack of recognition that storing and accessing data costs money. I mean, we have heard that. We heard that from Alex. We've heard that over and over again. You want data to be open, but you can't just tell people to open up data and not provide them with the resources to do that. So our policy challenges, and we've had challenges with our membership of the IVOA, although everybody in principle agrees it's a good idea. It isn't currently happening, although it did some years ago. And the problem is really a matter of priorities and recognizing that funding needs to be allocated to these sort of things.
Can I also add something to that? I think one of the things that it can sometimes be a challenge is, governments really want to support, the cutting edge research of researchers in their country. But of course, as we become more international and collaborative, it may be the case that I need to build a data center that will support a project that is not Canadian, but it is international. And sometimes I find what happens is that you need to, as Patricia said, argue that you really need money for storage, which isn't maybe as attractive as building a new telescope to a government. And also you might need to say, I need to put this infrastructure to support a much larger project where it cannot be said that one Canadian group will be doing all of the analysis or all of the research, that is collaborative. And I think sometimes astronomers need to do a little bit more work to kind of translate that language of international collaboration to some of our funding bodies who actually prize, national celebration, which can be tricky.
That's a good point. I think some of our advantages in collaboration have actually come from the international links, and particularly from the drive to collaborate with Europe, where, as Mark has mentioned, there are already very strong policies about the openness of data. And because they require it, it makes it easier for us to build it into our systems. So the international collaboration certainly helps drive openness of data because there is an interest in international collaboration. Perhaps it's the same for you.
And our panelists come from different countries, different continents. So are there best practices for data access that could be shared across nations? And do national funding agencies require open access to data within a certain time frame?
In France, there's a very strong push now that all researchers who work for the National Research Organization, CNRS, they have to make their publications open access, and they've put in place a system that allows you to do that, and even addresses some of the issues to do with publishers who would not normally allow that. So there's kind of legal basis for really doing open access in France, and it's a bit messy, but it's working. So there's certainly a national level policy about that. And I think one of the keys for describing this sort of thing is making the language accessible to everyone. So I'm kind of pleased that the policy direction has gone and there's a few documents in Europe associated with the European Open Science Cloud, and they use this acronym FAIR, findable, accessible, interoperable, reusable. And it just means that we're all talking the same sort of language. So when you talk to a biologist or a chemist or someone in social sciences, when we talk about making data fair, we have a kind of uniform, at least we're speaking the same language, whereas 10 years ago, we might have been talking specifically about, IVOA protocol for this or that no one else would have understood. Whereas now we talk about open access and fair, and it's making it easier for people to get on board, at least with the principles about that. So I think having good language is one of the best practices for enabling sharing of data and understanding of what it means.
Look at the Australian Research Council's guidance on open access today, and it's interesting that there is a requirement that publications are open access within 12 months if they're funded through the Australian Research Council, which is our primary method for funding science projects and therefore astronomy projects. And they use the word research output, but they also state that research data is not a research output. And I think that's an interesting legacy item that maybe is not really reflective of the value of data today, and that creating data that is valuable for others to use is equally important as writing a paper about it. However, there are at least an expectation that you will have a research and data management plan. It's not mandated that it must be there. It's certainly not part of the assessment, but it comes in for successful projects in the agreement that they must be doing something about it. So I think there's a little extra step to be taken, but again, as Patricia was saying, you can't just ask an astronomer in any research project, you created some data, make it open access, please. Yes, but how am I going to afford to do that? So we have a number of other schemes that at a national level provide some of the tools that general researchers need to do that. Things like minting a DOI, a digital object identifier for your data, and all these other sorts of things. So I think the pieces are kind of there, but maybe they're not as completely well joined up as they could be.
Yeah, how about for South Africa?
For South Africa, there's at the moment the requirement is only just coming into law for publications to be open access, and the data associated with publications must also be made public. But we're some way from treating, as I said, treating the rest of the data. What's the situation in China, Chenzu? How does it work there?
I'm planning to give some information from China. In 2019, the Chinese government established 20 national scientific data centers, including astronomy. Astronomy is one national scientific data centers. So the purpose to establish these data centers is to push the open access for the data in different scientific research fields. Currently, there have been some policies from the different level of governments, including the central governments and the local governments, and also the funding agencies, for example, the NSF China. Currently, middle-sized to large-scale sized projects are required to archive their data before conclusion of the project, and they should define a time window for their priority period for their data. And then the national data centers will keep this data, and the PI of the middle or large projects should design their data managed plans for their projects. So I feel in China we have a very good situation to push forward this the open access for both project data and the telescope observation data. For example, the sky survey projects. Yeah, maybe they are not special projects, funding projects, but they will produce data for a long time of period. So as Alex Sally mentioned, the SDSS project, we have Lamos the sky survey and some other. We also involved DESI and some other sky survey projects. So these observational projects will release their data as well as other funding agencies projects. So this is the situation from China. Yeah. Rini, can you say something about Canada?
Yes, sure. So if you are proposing for big national grants to support either building infrastructure or have science projects, we actually are required to have a data management plan within our proposals, and the proposals are evaluated on scientific and then on these different goals. We're also required to have discussions on sort of equitable access and equity and diversity and inclusion in our grants. This is something that's only started happening in the last couple of years. So it includes a focus on openness, but also how we're going to disseminate those results and kind of repair some of the imbalances in previous previous grants. So it's good. It's challenging, and I think a lot of people, there's sometimes a lag between the understanding of the researchers in terms of what is expected. But I think that because the push is coming from the governmental side, I'm very pleased that it will bring all of our scientists on board sort of by fiat.
Yeah, it seems open access is a trend for the global world. And at the same time, there must many challenges for this for these opportunities. So the next question is, what raw data products are made available in your field, and is data heavily processed or curated? Are there plans in place for data curation and archiving?
I think this is really interesting question, and particularly because it also relates to what Alex introduced in the talks. I know that in many fields there is a real trade-off starting to happen now between processing. The SKA is an example of it, just will not be able to save all the data, and so you have to make decisions now about how you determine if something is interesting before you save it. And Patricia mentioned the sort of alerts that will be coming from the Rubin stream. We have a challenge not only in terms of what data are saved and given to scientists, but how quickly they are made available. Because if you're looking for something interesting, it may be the case that you want to know within the first minute or two that it's detected in the sky, and so that pace is pretty challenging. But I do worry that in some cases where there is a lot of processing, that you won't be able to go back and infer if there were any issues in the analysis or processing. And so in those cases, I think you need a much longer or more sophisticated time of commissioning the telescopes to make sure that the choices you are making don't have downwind consequences that you can't go back and reprocess. So I think in almost all of our astronomy surveys going forward, the absolute raw data will be much more difficult to obtain, and most things will be either added or processed just because of the volume rates.
some of the early knowledge I'm building up on Earth observation data, it's interesting to look at things that communities do similarly, but things that are quite different. And so for those who aren't familiar with Earth observation remote sensing from satellites, what you are measuring is a value essentially of what was happening at ground level, but it's propagated through the atmosphere before you detect it. So they have this concept of analysis ready data. What comes from the satellite goes through a whole lot of pre-processing, and it's that analysis ready version that goes into the archives or the public resources, because there's a big community that doesn't care about how or what was done to the data. They simply want to use it for their particular application, whether they're trying to detect bushfires, measure the extent of flooding, trying to understand differences in deforestation, etc. So that analysis ready product is the main thing. But if you want to try other algorithms and other approaches, you can then go back through all of the other levels of data and get that original raw satellite image. And I think that's sort of kind of what happens in astronomy, but over a much longer period of time. And those sort of proprietary periods of having, in some cases, 12 months to work with data before it's made available, versus again this time domain and instantaneous transient world of the image has just been taken and here it is. And so I agree absolutely with Renee about the issues on the decisions that you make at one point in time may have consequences then that you go back and wish that you'd made different decisions, and it's not necessarily easy to work out how to make that possible at the very large scale. What sort of pre-analysis, Patricia, happens with some of the transient pipelines that you think about?
I can't actually answer that for the transient pipelines because things are not fully developed. There is a pipeline for processing the spectra from the Southern African Large Telescope, and that material is archived as well as the basic data. But the amount of data that we have, even from the Southern African Large Telescope, is small in comparison with the kind of quantities that people have been talking about. I think the full database is about 40 terabytes. Now that seems a lot to us when we're trying to, pay to keep it up, but it isn't large in international terms. The data from the Southern African Large Telescope is probably better archived than anything else that we have in the optical side in South Africa, because it's an international collaboration. But then there are complexities because different partners in that collaboration have different views about when the data should become public. Those involved in Europe have very specific requirements. The South African data becomes public at the moment, I think, 2 years after the semester in which the last observation of the program was taken. Some of the data for some of the partners never becomes public if they don't want it to become public, because they're private universities in the United States, and they don't necessarily have to make it public if they don't want to. There's very different philosophies on this. We are, and I'm not directly involved in this at all, we are working on archiving the data from our other telescopes, and I'm sure that the intention is to eventually make that public, but there is, as far as I know, no mechanism for doing that at the moment. And that may be driven harder when legislation comes into force that requires data to become public. But I think we are some way away from that as yet, probably years away from that, unless there's suddenly a huge push in order to join something that requires it.
With the passage of time, does it become increasingly difficult to even remember what was done to the data? Many people will have left the projects and so forth. So there's an issue of provenance and how that's put into these projects.
Yeah, I think that's a big issue with particularly with non-survey data. I mean, survey data does tend to be somewhat more uniform, and it's either accepted as part of the survey because it's good or not. But with data obtained by individual observers for a specific purpose, perhaps under poor weather conditions or whatever, I think that it is a problem as to whether it is good enough for doing whatever you want to do with it. And I guess the onus is for people to try, as long as the people are around who originally did it, to talk to them about it, and as long as they remember, of course, that is another issue. Yeah, that's a big issue with these kind of general archives.
I guess I have a question for that. Just having sat on the telescope allocation committee for some smaller telescopes, I wonder if, we as a community should start making some community decisions, such, so like if you haven't released your data, N years after it was taken, then you're penalized if you want more data on the same telescope, or, even if it is for a different project, so that we maybe create a self-regulating mechanism. Because my big fear is that when the surveys come online, the incentive for individual groups who are making observations that could be pivotal to the science, I worry that the incentive will be zero, because the surveys exist, and so in a sense they've taken some of that focus off the individual observers. But I don't know, maybe I'm being too worried.
Well, there's also the argument as to whether that data are valuable or not. There are people who would say, well, it doesn't matter. And I think we heard something about that in the previous talks. And sometimes it doesn't matter, but sometimes it does. And again, it's quite difficult to distinguish between those two things.
I would hate to see new barriers put in place that prevented people from reapplying, and I understand the purpose behind such an approach, but often then that can remove willingness to have very high risk projects, and perhaps that's as we increasingly go into eras of big surveys, some of the other instruments are there about doing the really risky things that we don't think are going to work, and so therefore the reason data might not have been published was that a high risk thing didn't work. And so that shouldn't prevent you from applying again. But yeah, it's a very interesting point for time assignment committees, and that's why I don't ever go on them.
So we just mentioned the data archives, and we also mentioned the pipelines. So there is another important topic about software. So next question is, to what extent do you make a code open source in your country?
Perhaps I can launch into that, saying that it has been very controversial here. I think it's becoming less so, but there has been pressure from our funding agency for astronomers to try and make a profit from code that they have written. There have been issues that well, we're putting a lot of money into you. Surely there are things you can do that are sell. And if you can't sell your data, at least you can sell your software. Now, astronomers, being astronomers, are extremely resistant to that and point out how much we have benefited from internationally freely available software, things like AstroPi, without which much of our work would not have been possible. So we've come from facing that argument to now drifting into the, well, you must make it freely available. And I think we're just trying to recover from the you must pay for it to the you must make it freely available, and we're not there yet. I don't think there's any particular. I mean, people do from time to time get involved in making changes to and additions to AstroPi, and again, I don't know the details of what everyone is doing. But I don't think there's any general policy that our data, our software code should be released. It's a very interesting question, though, and I'm interested to hear from the others what their national views are on that.
Yeah, just now, Alex Zali mentioned currently pipeline or software platforms are more and more professional. Usually, the codes developed by graduate students now is not good enough, and maybe the source code will be more and more professional, and yeah, very important or valuable. So maybe, or do you feel it is easier or harder than data for open source and open access?
I think it's a lot easier to share open source code now, and I've worked on a number of bespoke software solutions over my career, and many of my students have made code available. And sometimes early on there was a project we worked on where we actually had a commercial aspect to some code we had developed. So we made the libraries and the compiled version free. But if we had revealed the source code at that stage, we would have lost all of our commercial opportunity. Now, as time went on, the commercial value of that diminished, and as soon as we had no more commercial opportunity there, we're very happy to make everything open source. But a lot of very specialized code really only works in one circumstance. And so making my code open source, if you don't also have the same processing configuration and the same local data set and everything else, there's an educational value in seeing how other people write codes. But I'm sort of very much still on the fence about whether anyone should mandate that my code should always be open source. I think what has changed significantly is recognition for writing code, and that's been fantastic to see that come through the discipline. 20 years ago, trying to write papers about code and sending them to journals, you would be told you couldn't do it. Now we have journals that are dedicated to publishing and supporting code, and that's one of the ways that we can retain a workforce that we need in order to do all these very complex things for us, is to make sure that they're recognized through publications and other outputs as well. And it's the code is what they do.
Yeah, just to second that point, I do think it is having journals that publish code and having that recognition that you can write a paper that just presents a new code that doesn't have to also present a new science application has been really transformative, because there are some students and postdocs who maybe are transitioning, as you said, Shinzu, they're writing some code that's being supplemented by more professional work, but it naturally provides a really interesting link, I think, between more professional coding people and environments and graduate students, and also provides a little bit of training that now that you can actually focus on the code as the product and not some science application, which would be separate.
Okay. Yeah. Thank you. Thank you for your comments. Yeah. And we mentioned the date, and now we talked about software. So there is another very important element for science, that is computing source. So to what extent does your field provide computational resources to run pipelines on data sets? And how do we ensure access to data across nations with different amounts of computational resources?
Yeah. I think a really interesting example of this has been the Rubin Observatory, which is referenced quite a few times. So, so Rubin is this big $1 billion project that is being constructed in Chile. It's a partnership between the USA and Chile. And but obviously there will be international users from across the globe. And one way that Rubin is asking people to, in the international community, to provide in-kind contributions, one of the ways is through computational resources, so actual centers to process some of the data, but then also data access centers. And they provided a really good model for how those data access centers should be operated and the specifications for storage and processing. And then they also said, well, this will translate into data rights for your country. So it's a way to engage everyone in the operational support, because I think typically, operations and archiving and maintenance is, as Alex said, it's really critical, but it's not always something that is attractive to the people who are building the telescope itself. I think time will tell how those data centers work really well together and interface with the main US data facility for Rubin. But I think this is a really interesting distributed model, and is a good sort of preparatory framework for the much larger and more ambitious square kilometer array, which of course, again, has these separated distributed processing centers, just because the volume is so large. It's going to be so large.
Renee, can I just check something with you? That code will all be open access. Is that's my understanding? Is that correct?
That is correct. Typically, in order for your contribution to be received, it has to follow the standards of the science collaborations that are using it, and all of those science collaborations have open source at their heart.
So in Australia, we have a number of different computational resources that are available to the astronomy community. And I just want to quickly talk about three of them. So we have in Western Australia, the Pawsey Centre, which is very closely bound to the Australian SKA Pathfinder. It is the facility that does the processing to create useful data. But it's also a shared facility with other users, and so all of the processing time is not purely for astronomers. Then we have in Canberra what's called the National Computational Infrastructure. And so it's probably, I think it's a more powerful overall supercomputer than Pawsey, but it's mainly used for computational activities, theory, simulations, and so forth. So it's not co-located with the data. As we were talking at the start about the difficulties of transferring data around, if you wanted to do something clever with data that was sitting on Pawsey, well, you might have to move terabytes and terabytes of that across, and that's not sensible necessarily to do. But the other facility we have that's sort of a bit more open to experimentation is one at my own university, Swinburne, and it's we've had a long history of doing supercomputing locally, and being able to update and upgrade that facility every few years in terms of the types of processors and the size of the storage gives us a nice sort of intermediate. I think as soon as you have a national facility that you have to apply for time on, or you have a facility whose one of its main purposes is to make sure a telescope operates, then it does remove the opportunity to do experimentation. And that's possibly another risk as we go into the future, and particularly thinking about increasing the number of countries and astronomers who are able to access data, is that they may be locked into a situation where they can only ever use the processing that exists where the data exists. And so we need to think carefully about how we can continue to make sure that we can experiment with new ideas, but then somehow deploy them in an appropriate fashion.
From my experience from the National Astronomical Data Center, data storage, the cost for data storage is limited, and I can give a specific or detailed plan, budget plan. But for computing resources, it is very hard. For a very simple code, maybe it will cost a large scale computing resources. So for costing policy, for different national computing centers or data centers. How do we address the budget balance for computing resources? Do you have any ideas?
There almost needs to be some sort of market where we each get allocated an amount of processing, and I can trade it to you, because if I don't need it, someone else could use it more valuably. But I think that's a fairly frivolous comment near the end of a panel.
So one of the things in Canada that that happens is, so we have recently applied for a grant to build a large data center for processing SKA precursor data and Rubin data. And one of the requirements is that you don't build a very large computational infrastructure that is not connected to the various national research architectures. And so, you know, they're sort of trying to say it may be that you need to do a lot of your own processing, but if you're integrated into the larger, one of the larger national centers, then those nodes can still be used when you're not using them. And I think that it's been a really interesting way. And we're, with our particular framework, we're trying to explore increasing the cloud infrastructure of computing in Canada to try and help with that distributed nature. Because you're right, actually, Chris, like, you know, take some of my cycles when I'm not using them, I think is a pretty good model for how to do this. But you're right that it's very costly.
In South Africa, we have the Inter-University Institute for Data Intensive Astronomy that's been mentioned several times, and that uses cloud computing resources. It's largely used by the radio astronomers, but other astronomers also use it for simulations. And it's also used by the biology community quite extensively. So it is spilling out into these multidisciplinary reactions. Unfortunately, the South African Astronomical Observatory cannot afford to buy into that. So it's actually not particularly useful for our scientists. We pipeline our own data, and we provide pipeline data from SALT for SALT users. But there is again, this resource problem for the National Observatory, even in that sense. But IDEA seems to work very well for the university astronomers doing radio astronomy reductions, and some magnificent results have come out of that.
Yeah. Okay, thank you very much for your input. And we have 5 minutes left. And so I have other 2 questions. The first, the topic, the theme of the conference is for sustainable development. So how we need to reduce the carbon footprint of data storage and computer usage. So how can we do this?
It's been fascinating and to see the growth in interest in sustainability across all practices in astronomy, and a number of enlightening publications from the last few years, particularly from our early career researchers, looking at, you know, how can we reduce our overall footprint. Reduce your travel is obviously the biggest immediate impact, but the cost of computing, I think, you know, Alex has shown us the difference between cost, price, and value, and there probably needs to be a fourth element to that, around that sort of carbon neutrality in there. What should I really go ahead and do that computation? At what point should I have a little bit more education and training, and make sure that I've tested my code in an appropriate fashion before I go and deploy it? Because we were talking about the, you know, observations that are taken and then not ever published or used. Well, it's perhaps even worse if we're burning a whole lot of electricity to do a computation, and after, you know, days of running on hundreds of nodes, it just fails completely. And we didn't put any checkpointing or anything else into it. So I think that's the tricky thing for me, is I simply don't know how much it costs, and maybe there's an opportunity there for some more understanding with the various institutions of what does one CPU hour cost in terms of the carbon equivalent.
I don't know the answer to this. I do think we need to put more resources into making these things more efficient. And that's not just for astronomy. Obviously, that's for everybody who uses computing resources. So it's not simply up to us. But I think astronomers are concerned about global warming and carbon footprints. And maybe the onus is on us to take leadership in this area. It would be interesting to know what kind of government legislation would actually help us with that, rather than just make life more difficult, which would be very easy to do by clamping down on using of computers. But I don't know what the answer is.
From
There
an
was
archive. Yeah, Renee.
Sorry, no, I would just say I'll put in the chat. There was just a really interesting paper that was released only a couple of months ago on the environmental impacts of research in both high energy physics and astronomy, and they have some really interesting graphs about, you know, the basically said if you average over the costs of building telescopes and costs of running them, and you divide it into the number of astronomers, it's basically about 32 carbon tons, where we really want people to be at around 2. So we really, as astronomers, have a much larger impact if you factor everything in. And so they make some recommendations exactly for you know, greening up the telescopes themselves and powering them particularly, but then also for the computational resources. I think benchmarking codes in advance, as you mentioned, Chris, is one way to do that.
There's possibly some cleverness to happen around archiving as well. And at the moment, we have I think a desire that the disks are constantly spinning, so that any bit that I might want to access from an archive, I'm going to get it instantaneously. Whereas if we think back to the old days of tape drives, that it would sit in your cupboard until you actually needed it. And so the carbon footprint of an exabyte tape in my cupboard is essentially 0. So there must be some clever AI that can understand usage patterns of particular types of data and be more proactive in perhaps not having as much of it as live, as long as we know that it is there, so that if you perform some kind of a query, you may just have to wait a little bit longer to get it. And so it's trying to get that sort of the what data needs to be live constantly versus what data do we not want to lose, and we should do everything we can not to lose it. But if no one has looked at it for some number of years, there's a likelihood that no one ever else will look at it again. But that's not a reason to throw it out.
Yes, thank you. So our time is running out, but I have the last one question. Actually, can we take 2 more minutes? Okay, thank you. So about the global astronomical data, given the complex data size, so can we, how do we mitigate against the material being abused and given rise to misinformation or simple wrong answers when everything is open access? Data abuse or misunderstanding, misinformation.
We're in the era of generative AI, and it won't be long before someone tries to create survey or other observational data artificially and tries to pass it off as the real thing. And that's quite a confronting and terrifying thought, that's now everything you need to do that is now in place. I had a quick look on ADS this afternoon, thinking about blockchain and where is the opportunity within sort of blockchain for us to have some more security and provenance. And there were only 8 astronomy papers the ADS thinks are about blockchain, and only about one of them really is about a distributed style thing. So I think there's something in there. I'll take 10% of any commercial value that comes of blockchaining provenance of astronomy data. But I think there are some mechanisms that might be possible. And the other is these new approaches that aren't very good at the moment, that are also AIs that are able to detect whether something is real or not. They don't work terribly well. They can't solve all the problems, but we may just need some more layers of analysis that occur first of all to really convince ourselves that some sort of image is real before we commit it to an archive for some sort of pipeline processing.
Yeah, I think that's all good points, Chris. I think we have to keep in mind that this is possible. And it's been quite damaging to the biology community to see the number of falsified images that have been published and had to be withdrawn. People have a sort of trust in astronomy at the moment, which could actually easily be broken. Alex kept mentioning trust, and that's trust within the astronomical community. But if we lose the trust of the broader community, the taxpayers who support us, we're really going to be in trouble. So I think we have to be very, very careful about this. And that's all I can suggest, is that we bear in mind it could happen, and we try and try and avoid it.
Okay, so limited by the time, we have to stop here. And we also received 2 questions from our audience, but maybe I just read the questions, but maybe we didn't have time to discuss this now. So first one is about how is background data, which can be extracted from the same field, deal within archives. This is very important for UV and X-ray data. And another question is it thinkable that some supercomputing facilities will be made available to the community at large in a competitive way? So thank you all for the discussion. Thank you. So it's time now, Ashi, it's your time. Yeah.
Thank you so much, Shenzhou, and all the panelists. This was a fascinating discussion, and it brought up many, many interesting points. And I'm sure they will be covered in the white paper as we put that together. So thank you, everybody. It was a great session in general. And so that concludes the second session. And the final session, which is composed of 2 sub-sessions, will begin in just under 5 hours from now. So, and Pranav will be running that. So see many of you there, and the online participants. Thank you so much again.
Thank you very much for organizing this.
See you later.
Everyone.
Bye.
Bye.